Let's go. Okay, where are we going? We are headed towards my thesis. My thesis. My thesis. So I want to read for you, with you, next to you. We read e-commerce search fundamentals, and now I want to read Diego's. Read Diego, the other one. Siguru come to. That's it. Counterfactual, learning to rank via knowledge distillation. What is distillation? So first task we have is open, not Spotify but Speechify. Then we want to check the meaning of distillation. We have distilled water, right? Is it like cleaning the water? E-commerce search. Okay. Now I am ready to share with you my whole life. Where is it? Okay. Distill.
References.
Shut
1
up.
T. Joaquims. Ace
Shut
Nothing.
up.
T. Schnabel. Unbiased learning to
No,
rank with
it's too
biased
early
feedback.
for you to talk.
In Proceedings of the 10th ACM International Conference on
Dude, today I want to just have a fast review of the shit. Let's get it in once. We go over it in detail another time. I want to do it like that. No, it's also, the paper is published by Ehsan, eBay search ranking and monetization. What a fantastic, spectacular group. It's amazing. That's where you want to be in your life. If you are not in eBay search ranking and monetization, guess what? You are a loser. Or everybody is eBay search ranking and monetization, or they want to be in eBay search ranking and monetization. That's what it is. All right.
Counterfactual learning to rank via knowledge.
Wow. I'm just curious about counterfactual. So, what is counterfactual? Counterfactual is, if, I guess that's my interpretation. What would happen if this mouse or this phone was not here? Like when the phone is here, I get distracted, right? All the time. But what if the phone was not here? Would I be distracted more or less? I think that's called counterfactual. But knowledge distillation, something I have no fucking idea, because I don't even know what distillation is. Oh wait, what? Oh. Do you have me? Yeah, you have me. Okay. Distillation. Distillation. The action of purifying. Exactly. A liquid by a process of heating and cooling. How does heating and cooling? It's like separating alcohol from water. That's it. Yeah, okay. I know what the word in Persian is. The petroleum distillation process. Yeah, they have these towers and everything evaporates based on the temperature that they have, right? We know that. Then what is the opposite of evaporation? Then they snow. Snow. Solidify. Oh no, not snow, rain. Right, they rain. When a vapor turns into liquid, what is it called? Vapor, gas, not vapor. Gas turning to liquid. Condensation. Makes sense. Nice name. What if it turns to solid right away? Over consult. Deposition. Interesting. So we have distillation, which is evaporation and then condensation, and we have snow, which is deposition. The action of purifying a liquid. Wait a second, what if a solid turns into solid, turn to gas, solid to gas? Sublimation, sublimation or sublimation? Physical changes. Is it called physical changes? Oh, okay, we have a graph here. Okay, let me see. Solid to gas is called phase. Oh, okay, which one of them is called phase? Images. So what is happening? So plasma, fuck plasma. Plasma is too much for today. Yeah, let's go easy. So solid to liquid melting, right? That's easy. Solid to liquid melting, liquid to solid freezing. Okay, I saw it, but I knew it. Liquid to gas evaporating, gas to liquid. Gas to liquid was condensation, evaporation, condensation, perfect. And this is the weirdest ones are gas to solid, which is gas to solid, I just said deposition, and solid to gas is gas is sublimation. Why should it be sublimation? Deposit. Deposition comes from deposit. So we are oxygen depositing into. Why should it mean? What does sublimation? Sublimation. Can you pronounce it? Psychology? Pronunciation.
Sublimation.
Sublimation. So sublimation was solid to gas. What is solid to gas? Example. I think there were some pills that, yeah. Ice sublimed away. No ice sublimes.
Sublime.
Oof.
Sublime.
What a nice voice.
Sublime.
Really, guys, you should go try it. This is different. I don't like this voice. Can you pronounce?
Sublimation.
Ah, it's good, but look at this.
Sublime.
Oh, she's the same person. I like my iPhone more.
Sublime.
Yes.
Sublime.
Try it on your iPhone and let me know how it works. Oh, actually, I have Android. Oh, on Android and iPhone is the same. So, okay, perfect, sublime. Oh, we started because distillation was the process of first doing evaporation and then condensation. And now we wanna distillate knowledge, right? Let's go, brother.
Distillation.
Ehsan, show us how do you
Ehsan Ibrahimzadeh 1, Alex Kotzi 1, and
Distillate.
Abraham Bakverjiran 1,
or distill
Abstract knowledge distillation is a transfer learning technique to improve the performance
But I
of a
wanna just,
student
as I
model
say, I
trained
wanna
on a
hear
distilled
you.
empirical risk, formed by a label distribution defined by some teacher model, which is typically trained on the same task and belongs to a hypothesis class with richer representational capacity. In this work, we study knowledge distillation in the context of counterfactual learning to rank, LTR, from implicit user feedback. We consider a generic partial information search ranking scenario, where the relevancy of the items in the logged search context is observed only in the event of an explicit user engagement. The key idea behind using knowledge distillation in this counterfactual setup is to leverage the teacher's distilled knowledge in the form of soft predicted relevance labels to help the student with more effective list-wise comparisons, variance reduction, and improved generalization behavior. We build empirical risk estimates that rely not only on the debiased observed user feedback via standard inverse propensity weighting, but also on the teacher's distilled knowledge via potential outcome modeling. We analyze the generalization performance of the proposed empirical risk estimators from a theoretical perspective by establishing bounds on their estimation error. We also conduct rigorous counterfactual offline evaluations as well as online controlled randomized experiments for a product search ranking task in a major e-commerce platform. The primary distinction of the proposed distillation-based perspective in contrast to the standard counterfactual inference based on potential outcome modeling is that we leverage teachers trained on different, yet related, tasks to improve the generalization power of a student model for a ranking task. Specifically, we report strong empirical results showing that the distilled knowledge from a teacher trained on expert judgments can significantly improve the generalization performance of a student ranker. We also show how explanatory click models, trained for a click prediction task with privileged encoding of the presentation context in observational data, can explain away the effect of presentation-related confounding for the LTR model. Keywords: learning to rank, counterfactual inference, knowledge distillation, potential outcome modeling, doubly robust estimation. 1. Introduction. 1.1 Motivation. Learning to rank, LTR, from implicit user feedback is the predominant approach in large-scale information retrieval systems, where search
Oh,
context
dude, guys,
information
this is amazing. This is what actually the other paper which Diego sent us was about. Feedback from implicit user feedback. Okay.
and user engagement
Implicit,
events
not
are
explicit.
constantly logged and are available at desirable scale, granularity, and recency. User engagement events on the search engine result pages, SERP, are driven not only by the underlying search ecom24 intent, but also through the presentation context, governed by the slotting and organizational policies of the search engine. Specifically, in a list-wise presentation of the search results, users are more
What is the
likely to
difference?
engage with higher ranked items.
Is there a difference? Slots. Okay, let me share. Slots.
Slot.
Okay. Lot.
Slut.
What is the difference? I don't get it.
Slot.
This is a slot.
Slut.
This is a slot.
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 Slut.
It's a bit different.
Slot.
Like it's a slot when it's a slow motion. But this one is slot.
Slut.
Slut. I think this one is shorter. Slut. Short slut. But short slut is this slut.
slot,
Slot. Yeah, this one is like more stretched for sure.
slut,
Slut. This is shorter. Slut. Fucking slut. Then you say slut and then you hide. That's it. So what is the other slut? What is the biggest slut? No, I don't wanna ruin my YouTube with this bullshit. Okay, fuck that. Let's go.
Due to their inherent sequential browsing of the page. This signifies the so-called position bias in SERP level user engagement events, which in turn implies that it is more likely to observe the relevance of the top ranked items in the logged SERPs than the items ranked in lower slots. The standard approach to account for the inherent presentation bias.
Fuck off. CRP is search engine ranking prioritization or position. What is this ERP? SERP. Search engine result page. Okay.
This signifies the so-called position bias in SERP level user engagement events, which in turn implies that it is more likely to observe the relevance of the top ranked items in the logged SERPs than the items ranked in lower slots. The standard approach to account for the inherent presentation biases in the observational search activity data is to adopt the propensity matching-based counterfactual inference framework 1. The key idea behind this perspective is to hypothesize an explanatory click model based on causal constructs that govern users' browsing behavior to and estimate a notion of observation propensity as the probability that the user examines the relevance of an item.
Propensity and probability are next to each other
in a given search context. The estimated propensity scores are then used to build a debiased empirical risk estimate using a technique called inverse propensity weighting, IPW. Note that,
IPW?
Unlike the standard causal inference settings for estimating average treatment effect estimation, the examination event, which signifies the Note that, unlike the standard causal inference settings for estimating average treatment effect estimation, the examination event, which signifies the treatment in this formulation, is not fully observable, and we need to make strong assumptions to build reliable chronicity score estimates. On the other hand,
can you shut up? Dude, I want to listen to this shit. Note that unlike the standard causal inference settings for estimating average treatment effect estimation. What is that? Note that unlike the standard causal inference setting. What is the standard causal inference setting? I don't know. For estimating average treatment effect estimating the examination event, which signifies the treatment in this formulation, is not fully observable, and we need to make strong assumptions. When we make assumptions, we lose some stuff, but it's good, we gain some stuff. To build reliable, do you remember the video we watched from the guy from Stanford working on OpenAI? Like, at the beginning you build assumptions, but at the beginning it's good, but once your model is good enough and your computational power is high, you need to remove those assumptions. Well, reliable propensity score estimate. Okay, let's go.
On the other hand, predicting the counterfactual probability of click in the absence of presentation context confounding is a hard problem. While there is a rich literature on developing predictive and descriptive click models based on distributed representations of the search context, e.g. 3, or the confounding click.
Guys, to be honest, I am the head of mental masturbation. There is no doubt. Nobody is more mental masturbator than me. I am the head of it. There's no doubt. And it really fucks me up. I need to focus now on this. Oh my god. I got acne everywhere. Okay. I think I'm gonna read it myself if you wanna talk inside my head.
Models that disentangle relevance and bias modeling for or causal probabilistic graphical models to explain users' browsing behavior, e.g. the overwhelming body of research on unbiased LTR rely on slight variations of the IPW technique based on the so-called
IPW is
position-based
inverse propensity weighting.
examination model 5.
Yeah, okay.
1.2 contributions.
Guys, fuck it. Whenever it talks too much, like, you wanna, like, let it mental masturbate. I don't like it, but I think just getting into fight with mental masturbation is pointless. It just wants to get your attention. Okay, whatever.
Building reliable causal click models from observational data is challenging, particularly in the presence of heterogeneity in search context representation and user activity data. This is because for a predictive model to be contextually discriminative and well calibrated, one needs complex models with rich representations, while LTR models trained on a list-wise objectives can achieve similar ranking performance with cheaper representations. Despite recent attempts for building causal click models with richer encoding of the search context for disentangling the relevance from presentation-related confounding from observational data for 6, there is still fundamental theoretical gap to incorporate an arbitrarily complex click model in a counterfactual learning to rank setting with rank discounted information retrieval, IR, objectives. In this work, we address this theoretical gap by adopting knowledge distillation in a counterfactual LTR framework, where a relevance teacher trained on a relevance prediction task is used as a potential outcome model that helps improve the generalization behavior of the student model for the LTR task. Specifically, we study multiple empirical LTR risk estimates that are built via the distilled knowledge from a teacher model as well as the debiased observed user feedback through IPW. To improve the generalization behavior of the vanilla IPW-based and distilled empirical risk estimates, we adopt an array of diverse approaches, including the doubly robust technique 7, to build estimators that are robust to inaccuracies of either the teacher model or the propensity model. The doubly robust estimator for LTR is also developed in the excellent concurrent workaid. We present a theoretical analysis of the estimation error of the proposed estimators by characterizing a bias variance trade-off, which shows that well-calibrated teachers that approximate the Bayes relevance classifier generalize better. By introducing knowledge distillation in the partial information LTR setting,
what is this fucking knowledge distillation in learning to rank? Well, distillation means is used for purifying or separating two liquids from each other, right? So when they are saying let's distill knowledge, what it means? It means purify it, get rid of the shit. Also it means knowledge in its basic form is a liquid and it is floating from one place to another. What is a knowledge in a form of gas? Once we turn knowledge into gas, it turns into garbage. Knowledge and garbage. That's it.
Contribute to the growing literature on understanding the underlying statistical benefits of knowledge distillation. Our approach to employing knowledge distillation in counterfactual LTR is, however, different from the standard application of the technique, in that the relevance teacher is trained on a predictive/explanatory task, while the student uses the debiased relevance probability estimates of the teacher as soft training labels for the ranking task. Essentially, through teachers' distilled knowledge on unengaged items, the student can learn from more informative list-wise comparisons among all pairs of training samples in a query context rather than contrasting only the engaged items with the unengaged ones, as in IPW-based techniques. While our generalization analysis is generic, we discuss specific techniques for developing effective teacher models. In particular, we first discuss how explanatory click models that encode the page context confounding independently from relevance covariates help explain away the confounding presentation context in the logged search session 9.4, and propose simple deconfounding techniques to use observational data for training the relevance teacher. This is very similar in nature to the IPW-based technique discussed in A. Beyond counterfactual click prediction teachers, we also introduce relevance teachers trained on a different, yet highly related, task. We report strong empirical results on a ranking task in a major e-commerce platform showing that a teacher model trained on expert relevance judgments can significantly improve the generalization power of the student model.
Teacher, you
The
can help the
significance of this
student.
result is multifold. First, it offers a new perspective on knowledge distillation as a technique to incorporate heterogeneous sources of search utility to the user in training the ranker. Second, it offers an effective way to incorporate a broader set of queries, which may not have rich historic user engagements in training the ranker, thus alleviating the inherent selection bias of the rankers relying only on search S contexts with rich historic engagements.
What is search S
1.3
context?
Summary of prior art. Propensity matching the standard prevalent.
Okay. I wanna fucking stay awake! I wanna stay awake! Fuck it! I wanna stay awake and read paper. I wanna know summary of the prior art. I wanna know the summary. I don't wanna get into detail. Prior, it was an art. It was a knowledge. It was not science. It was a piece of art. Because we are all artists. That's
Technique
it.
in counterfactual LTR is the inverse propensity weighting, IPW, 1, where the observed biased clicks are appropriately weighted in the empirical estimate based on estimated probabilities for observing the item's relevancy in a given search context. In 10, it is shown that the IPW estimator fails to account for trust bias 11, which is
By
the
the
gap
way,
between
what I
perceived.
love about this paper, there is no fucking footnotes here, so that this motherfucking dumb fuck, stupid speechify gets reading them every time.
Relevance and true relevance that is often modeled
It
as
is
a
relevant.
position-dependent confounding, and new estimators based on affine corrections are proposed,
Correction.
which is adopted in
Correction,
multiple subsequent works 12, 13. Explanatory click models. The simplest, yet most popular, explanatory model is the examination-based click model 14, 5, defined by operationalizing the causal construct of observation as a latent examination random variable. The examination-based models posit that an item is clicked if it is examined by the user and in addition is relevant to the user's intent. It is often further assumed that the examination event depends on the search context only through the position of the item in the SERP. Examination-based models are enriched in various ways to incorporate more granular presentation biases given the search context. Most notably, 2 proposes a dynamic Bayesian network model, DBN, where new hidden variables are introduced to explain clicks and search abandonment events. More recently, 2 tower models for click prediction 15 with independent relevance and observation towers have gained popularity. The relevance observation factorization assumption is revisited in 6 and deconfounding methods are proposed in 4, 16 to disentangle relevance from observation. Propensity estimation. Standard click propensity models are often only based on the position bias 14 and there is a variety of techniques to estimate the parameters of such models based either on online interventions through randomization and interleaving 17, or likelihood optimization from logged data 17, 18. Intent-aware examination models are proposed in 19, 20, 18, where different click propensities are learned for different intent classes. A dual learning algorithm is proposed in 21 to solve the problems of unbiased learning to rank and unbiased propensity estimation simultaneously. Potential outcome modeling. The idea of using potential outcome models for counterfactual inference is popular in the context of contextual bandits and recommendation systems where predictive models for the reward are developed instead of or in conjunction with inverse propensity weighting scheme to build empirical reward estimates. 22, 23, 24. There are a number of recent works in the context of unbiased response prediction that leverage and analyze the doubly robust technique 25, 12, 26, 8. Counterfactual evaluation click models are widely used for counterfactual evaluation of IR metrics, either as data-driven rank discount functions in utility-based metrics or as estimates to the user satisfaction gain in effort-based metrics 27. The bias of the vanilla average overall evaluation metrics is studied in 28 and propensity-based correction is proposed for debiasing. Using predicted relevance probabilities as training labels has in fact been considered in 2.19, but it is only limited to settings where the adopted measure of ranking loss only depends on the relative order of the labels than the actual values. Knowledge distillation. There has been a growing interest in understanding the statistical underpinnings of knowledge distillation to explain its empirical success 29, 30, 31. Most notably, the closest relevant work to our study is 29, where distillation is studied from a statistical learning theory perspective by establishing a
What is
bias variance
distillation?
trade-off for the student based on the quality of the teacher in estimating the true Bayes.
Counterfactual evaluation. Statistical learning theory. Establishing the bias variance trade-off of this true Bayes. Fuck off. Chat.
Knowledge distillation is a technique in machine learning where a smaller, simpler model, referred to as the student model, is trained to replicate the behavior of a larger, more complex model, known as the teacher model.
Oh, okay.
The goal is to transfer the knowledge from the teacher model to the student model, allowing the student to achieve comparable performance while being more efficient in terms of computation and memory usage.
Makes sense.
Here are the key steps involved in knowledge distillation. Training the teacher model. First, a large and complex model is trained on a data set. This model typically has a high capacity and can achieve high accuracy on the task but is often slow and resource intensive. Generating soft targets. The teacher model is then used to generate soft targets for the training data. These soft targets are the probabilities output by the teacher model for each class, rather than the hard labels, example 0 or 1. The soft targets contain more information about the data distribution and the teacher's learned knowledge. Training the student model. The student model is trained using a combination of the original hard labels and the soft targets provided by the teacher model. The objective is to minimize a loss function that takes into account both the traditional loss, example cross entropy with hard labels, and the distillation loss, example Kuhlbach-Leibler divergence between the students' and teachers' output distributions. Optimization. During training, the student model learns to mimic the output distribution of the teacher model, effectively absorbing its knowledge. The result is a smaller model that retains much of the accuracy and knowledge of the larger model but is more efficient for inference. Knowledge distillation is particularly useful for deploying machine learning models on devices with limited computational resources, such as mobile phones and edge devices, where model efficiency is crucial.
Okay, we got it. So that's it. That was so easy.
Estimating the true Bayes class probabilities in a multi-label classification and retrieval. More recently, 32 extends knowledge distillation to top K ranking problem, where ranking at the top is preserved by matching the order of items of student and teacher, while penalizing items ranked low by the teacher. In 33, multiple distillation techniques are proposed to improve the generalization power of the trained recommender model using data from a random logging policy. A similar uniform data augmentation technique is used in 34 to guard against feature distribution shifts. A recent work that offers a similar perspective on knowledge distillation in LTR is 35, where the teacher has access to some privileged features. 36, that the student does not have access to. The other closely related works are the ranking distillation setting in 37,
I don't want to
38,
sleep.
where the
I
teacher
don't
model
wanna.
is trained on the same ranking task. The main distinction between this study and prior adoptions of knowledge distillation for the ranking tasks is that we employ teacher models that are trained on a predictive task and are meant to provide predicted relevance probability estimates to the student. 1.4 Notation. Here is a list of notations adopted throughout the paper. Sets and ordered sets, also referred to as lists, are represented with uppercase calligraphic symbols, such as random quantities are shown in bold, such as D with realization. The expected value of random variable C is denoted by C, and the conditional expectation of a random variable C equals R, O, given R is denoted
Can
by
you see that
CR.
patch?
For a measurable event, we denote by C a random variable defined in the measurable space equipped with a regular conditional probability measure, dot, with respect to the conditioning sigma algebra. For a function rightward arrow, the dimensional array, set membership symbol is denoted by
Denoted
2
by
background
F.
and problem setup. 2.1 Empirical risk minimization for LTR.
LTR, learning
We
to
consider
rank.
a
We are
generic
learning to
supervised
rank.
setup
We are
for learning to rank from
We are a
implicit user
teacher.
feedback
We
in
are
the
a
logged
student.
search
We are
activity
learning to
data.
rank. We are learning
A
to
logged
rank.
search
This
set
is the
membership
teacher.
symbol is
This the
characterized
student.
by the
This is
query,
teacher.
and the
This is
ordered
the
collection
student.
of items set membership symbol slotted by the search engine's ranking policy at the logging time,
Who
as
got
well as the
slotted
click
by
events
it?
attributed to the items on the SERP.
We consider a generic supervised setup. Supervised means we have X and Y. For learning to rank from implicit user feedback, which is amazing, in the logged search activity. I love implicit feedback because it is the most common one. A logged search S in S is characterized by the query Q. A logged search. What is a logged search? Q and the ordered collection of item DS in the end slotted by the search engine ranking policy at the logging time, as well as the click event attributed to the item on the SERP denoted by CDS in 01 to the N. So you can see that that was one sentence and I totally missed where the verb is, right? And the ordered collection of item DS in D slotted by the search engine's rank policy at logging time, as well as the click event attributed to the item. These are not use of language, dude. I'm not just, okay, by the way, I'm not criticizing this paper. All the papers are like this. My papers are worse than this. This paper has an application. My papers do not have any application. We just use big words all the time.
Denoted by set membership symbol 0, 1.
Okay, by the way, because I also write papers, it's not just about the reading. Like, if once a person is writing a paper, they try their best the paper to be readable. But if they want to really explain everything and use simple sentences, I bet the paper size will be twice, doubled. So, but that's the thing, like, on the one side, journals expect you to keep it short and concise. On the other side, you wanna tell the reader, explain it to them. To be honest, explaining something to another person takes time. You cannot explain in a very compact manner. So that's why reading paper is so difficult. Anyways,
It is standard to assume a preference model with the context item desirability distribution RS, that produce Oracle ground truth relevance labels. We adopt a simple explanatory model on the sequential browsing and examination behavior of the user that explains a click event on an item in the search context, C equals 1, based on whether the item on the SERP is examined by the user, O equals 1, and that it matches the user's underlying search intent, R equals 1,
Why can't they
asserting
read this?
C equals 1, equals,
What is
O
C?
equals 1, R
So
equals
okay. That's why once we get to mathematics, okay, this time we don't want to get into the mathematics. So let's read the stuff that is less mathematical. We just ignore the mathematics part. We get into the details of the model once again.
1.
Yeah.
1. The conditional probability, O equals 1, is
Let's
referred to
get
as the
to know
propensity
how
of
much we
observing
can
the relevancy
understand
of the
just
item in the
reason.
search context.
Like we were blind. Okay,
We
no,
further
blind
simplify
doesn't
the
count.
adopted examination
Wait a
model
second,
by
how do
assuming
blind people read from laptop, by the way? How do blind people use laptop to read or smartphone? That's so good. We have them for allow smartphones and other digital devices. Here are some of the main tools and methods. Okay.
blind
Screen
and
reader,
visually impaired people.
which we are
Screen
using.
readers are software programs that read the text displayed on the screen aloud using a synthesized voice. They also provide Braille output for those who use Braille displays.
Wait a second. How do they?
Some popular screen readers include
How do
NVDA,
they? What are they
non-visual.
doing?
They also provide Braille output for those
How do they provide braille output? It's just they have a printer on the side.
who use Braille displays. Some popular screen readers include NVDA, non-visual desktop access, a free and open source screen reader for Windows. JAWS, Job Access with Speech, a widely used screen reader for Windows, though it is paid software. VoiceOver, a built-in screen reader for Mac OS and iOS devices. TalkBack, a built-in screen reader for Android devices. Refreshable Braille displays. These are devices that
That's
connect to a
cool.
computer or smartphone.
This is not printer, but it's just can change. That's fun.
Refreshable. Blind and visually impaired. Refreshable Braille displays. These are devices that connect to a computer or smartphone and provide Braille output by raising and lowering pins in Braille cells.
That's so nice.
They allow blind users to read the text displayed on the screen in Braille.
Dude,
Screen
inventors
magnifiers.
are nice people.
Screen magnifiers enlarge text and images on the screen, which can be helpful for people with low vision. They often come with additional features like color inversion, high contrast modes, and text-to-speech functionality. Voice assistants. Voice assistants like Siri, Google Assistant, and Amazon Alexa can perform a wide range of
How
tasks
does
through voice
Amazon
commands,
know?
such as
Is
sending
it
messages,
the first thing
making
comes on
calls,
Amazon?
setting reminders, and searching the web.
Okay, that is not
Speech recognition
what I had
software.
in mind.
Speech recognition software allows users to control their devices and dictate text using their voice. This can be particularly useful for writing documents, browsing the web, and using applications without needing to see the screen. Accessible software and apps. Many applications and websites are designed with accessibility features that make them easier to use for people with visual impairments. Features like keyboard navigation, alternative text for images, and simplified interfaces contribute to better accessibility. Braille note takers. Braille.
Okay, okay, so there are some tools, that's nice. By the way, by listening and talking, it really helps, right? Maybe reading is a bit more difficult. Like if you're blind, you don't need to have this, like you always can have a tablet. Well, you don't need the screen. That's what it is. You can always have the keyboard. And to be honest, if you're a good typist, you don't need to look at the keyboard. So you have the keyboard, everything is computed under the keyboard, and you don't need to open your laptop. Like that is, they don't have a screen, so it's just a simple one. That's so kind of cool.
Model by assuming that the click propensities depend on the presentation context only through the position of the slotted item on the SERP by the ranking policy, that is, O equals 1, equals, O equals 1, 2. Where is the rank
Fuck
attributed to
mathematics.
item
Let's
by the
do
ranking
not look at
policy?
it. Exactly. That's what I want to see. Actually, this is good. Let's assume we're blind. Let's see how much we can learn from a paper, distill knowledge from a paper without looking at the math. And for us, the conclusion is what matters. For us, well, for this paper, to be honest, I want to get in the model and how like Ehsan works with the paper, how do they set up. I want to get to know that. But for paper, you don't want to get into the math right away. You know what the problem is, you want to get what the conclusion is in a non-mathematical
search context.
Actually, that's it. You have the problem, you distill it, which turn it into the gas, like evaporate it, turn it into the gas. In the gas space, we use mathematical equations. Mathematics is in the gas space. Once we got the result, we condensate it and do the condensation and do the liquid, which is the conclusion, which are again normal words, not mathematics.
There is a large body of literature on estimating position-based user click propensities either through online interventions or offline estimation techniques based on latent variable models from logged search data. The position-based observation probabilities, O equals 1 rank, define a rank discount function, rank, that explains the effect of the presentation context on the user engagement in the search context primarily based on the position of the slotted items, which one can approximate via fitting a univariate model on the estimated propensities as a function of the ranking slot. Given the adopted user behavior model and logged search activity data, our objective is to train a ranking policy by minimizing the statistical risk, corresponding to a search efficiency metric function, which approximates the expected number of user behavior events. Specifically, we define the statistical risk for a deterministic ranking policy, corresponding to a scoring function, that produces a score for each individual document set membership symbol given the search context, as equals 3, where equals is defined based on an estimate of the expected number of clicks in the search context via a sequential browsing examination model in the form of discounted cumulative gain, DCG, from the rank list, produced by the policy with respect to oracle labels, and the rank discount function. We note that DCG type information retrieval metrics are often defined as measures of gain, while with a simple sign tweak, we consider them as measures of loss for risk minimization. While our discussions of the search efficiency-based loss function are primarily from the perspective of a likelihood model on the data, we note that our framework generalized to any standard ranking loss function that is linear as a function of relevance labels.
Rounded rectangle.
Since the underlying joint distribution of the search contexts and relevance labels is not known to the learner, the standard approach is to build an empirical risk estimate. 1 equals sigma set membership symbol 4. Based on a sampled set of search contexts with suitably defined empirical labels, to approximate the ground truth label distribution RS. In order to characterize key statistical properties of an empirical risk estimate, we establish bounds on moments of the estimation error, which is the divergence of the empirical risk estimates from the base statistical risk, based on the divergence of the empirical relevance labels from the underlying relevance probabilities. Lemma 2.1.
Fuck off. Fuck
For
physics.
any ranking
I
policy,
say.
rightward arrow and non-negative
Fuck,
integer
I
comma.
lost it. Okay.
Less than or equal to S, R, S, S2 comma. Where equals
That's it.
equals
Sometimes
1
you
2.
want to do something,
The
it
proof
doesn't
follows
happen.
by invoking the towering
But
root and a
sometimes-
straightforward application of Cauchy-Schwarz inequality. Generalization bounds for empirical risk estimates
Actually,
can be obtained by
front finger doesn't matter at
invoking
all.
concentration
Well, it matters
techniques
a
like
bit, but
Bernstein's inequality, which characterize the
finger,
generalization
thumb is
behavior
finger.
of a policy based on the bias and variance of the empirical risk estimator.
I want to
There is a remarkable
move
body of
along
work
your
around developing
hand so
efficient
that the
algorithms
cube
for
feels
empirical
that
risk
you are with
minimization
it, so it
(ERM)
gives
on
it some
DCG-based loss functions over a
encouragement to
variety of
move on.
different
Look.
hypothesis classes.
Look at this. I
In
want
this
to move
study,
it this way.
we are oblivious to the choice of the
Did it?
hypothesis class and the particular optimization techniques adopted for training, and focus on the generalization power of the estimators as it relates to the estimation error,
That's really cool.
oblivious to approximation and optimization. Errors.
Enough.
2.2 Counterfactual LTR, debiasing via inverse propensity weighting. Given the examination model, 1, on the user browsing behavior, we assume that we have an oracle algorithm to estimate the propensity to engage with item in the search context. Once click propensities, O equals 1, are estimated, an empirical risk estimate can be built using debiased labels formed via the inverse propensity weighting, IPW, technique by simply setting IPW equals O equals 1, 5. We note that the underlying assumptions on the user behavior data for the propensity estimation task can in general be different/richer than the position-based model, 2, adopted to define the ranking efficiency task. While our discussion can be applied to arbitrarily complex propensity estimation techniques, to simplify the presentation, we assume that the propensities are estimated based on a vanilla position bias model, that is, O equals 1, equals 0, where 0 is the rank of the item in logged data. Owing to the linearity of the loss function as function of relevance labels, it is straightforward to show that the IPW empirical risk estimate, denoted as 1 sigma, comma, set membership symbol, is an unbiased estimator of the Bayes statistical risk given the examination model, if the estimated propensities are unbiased. The IPW estimator is known to have high variance, especially when the estimated propensity values are small, and there is a significant body of literature around clipping and normalization techniques to reduce the variance of this estimator. In this work, to improve the generalization of the LTR estimators, we introduce a number of techniques based on potential outcome modeling, and characterize their bias variance trade-offs. IPW 6. 2.3 Knowledge distillation. Knowledge distillation is a transfer learning technique where a student model is trained on a distilled empirical risk built based on a label distribution provided by a teacher model. Given a teacher model times rightward arrow that produces an estimated score for the relevance probability of each individual document set membership symbol given the search context, a generic distilled empirical estimate for the risk of the student can be defined as KD equals 1 sigma set membership symbol 7. As shown in the next section, distilled empirical risk estimates has desirable variance reduction properties compared to the vanilla empirical risk estimates based on observed feedback and inverse propensity weighting. As such, a straightforward, yet fundamental, observation to make about the variance reduction properties of distilled risk estimator is that Remark 2.2. The variance of the distilled risk estimator built based on the true Bayes relevance probabilities is no greater than the variance of the vanilla empirical risk estimate formed by realizations from the relevance distribution. The proof is trivial and can be found in 29.23. The improved variance in this estimator often comes at the cost of some bias, which leads us to explore hybrid estimators that take advantage of the observed user feedback as well as the teacher's distilled knowledge. 3. Debiasing empirical risk with relevance distillation. In this section, building upon the ideas discussed in the previous section, we propose empirical risk estimates that leverage the observed user feedback as well as the distilled knowledge from a suitably trained teacher. The core idea is to use the observed user feedback to improve the bias and at the same time use soft labels provided by the teacher to improve the variance of the estimator. We first discuss our proposed distilled empirical risk estimators oblivious to the choice of the teacher model and characterize their generalization behavior by developing bounds on their bias and variance, and then discuss a number
I
of
think they
techniques
have
to
a
develop
really good
effective
paper.
teacher models. 3.1 Distilled empirical risk estimates. 3.1.1 Hybrid distilled risk estimators. The main idea for building hybrid distilled risk estimators is to define a simple trade-off for bias/variance behavior of the estimator by a convex combination of the IPW and distilled empirical risk estimates. Formally, for a teacher times rightward arrow, some estimate of the click propensities, and any 0 less than or equal to 1, a hybrid distilled estimator of the risk HD, can be obtained by setting HD, equals 0, plus, 1, a in 4. Next, we analyze the bias/variance of this hybrid estimator. Note that the bias/variance analysis of the IPW and vanilla distilled empirical risk estimates can be derived as corollary by setting to 1 and 0, respectively. For a given search context, and a document set membership symbol at rank 0, let denote the actual relevance probability, R equals 1, and denote the actual propensity scores, O equals 1. Let us define the deviation of the estimated relevance probabilities and the estimated propensity scores from the actual quantities as delta equals and equals 1, respectively. 0. Theorem 3.1. For any student policy, HD, less than or equal to 1 DD plus 1, delta D set membership symbol 2, where 1 is the same constant as in lemma 2.1. The proof is straightforward and is followed by characterizing the bias of the empirical labels and invoking lemma 2.1. Please refer to the appendix for a complete proof. Theorem 3.1 provides insight on how to control the bias of the estimator by adjusting the parameter by trading off the bias terms due to the IPW and distillation-based components. The variance analysis in the appendix shows that the variance due to the IPW component is sensitive to small propensity score values and the propensity estimation errors. In this case, the variance reduction that we achieve by including the distillation-based component helps with better generalization of the hybrid estimator. 3.1.2 Doubly robust risk estimators. Although hybrid empirical risk estimates provide a simple and flexible way to control the bias-variance trade-off, they can incur significant estimation error if either of the risk components are inaccurate. To alleviate this, we adopt the doubly robust technique 23 to make the empirical risk estimator more robust when either of the risk components are accurate. Formally, for a suitable operationalization assumption for the observation event O, a teacher times rightward arrow and some estimate of click propensities, a doubly robust estimator of the risk dr can be obtained by setting dr equals plus 0, 9 in 4. The next theorem shows the double robustness property of the doubly robust estimator. Theorem 3.2. For any student estimator, dr less than or equal to 1 delta dd set membership symbol 2, where 1 is the same constant as in lemma 2.1. The proof is followed using similar techniques as in the proof of Theorem 3.1 and is included in the supplemental materials section along with the variance analysis. Theorem 3.2 shows the desirable double robustness of this estimator, where the bias of the individual terms will be small if we have good estimates for either the actual click propensities or the true relevance probabilities by the teacher. 3.2 Teacher models. Our discussion of the distilled risk estimators were focused on their theoretical generalization properties in terms of the estimation error oblivious to the choice the teacher model. The key Benefit of using knowledge distillation in counterfactual LTR is the improved generalization properties of the student, achieved through label smoothing via the teacher's distilled knowledge. While the student often has to satisfy stringent inference time constraints, the teacher model can be arbitrarily complex, not only in terms of the representational capacity of the hypothesis class, but also through leveraging features/representations that the student does not have access to at the inference time. Such features are referred to as privileged features in 35. In this section, we discuss generic techniques to develop effective teacher models, which we will exemplify in the empirical results section. 3.2.1 To confounding teacher. In order to train a relevance teacher using logged search data, we adopt the counterfactual inference framework based on potential outcome modeling. The fundamental inference challenge in this setting is that we are interested in counterfactual relevance outcome had the item was observed, denoted by R, O equals 1, while we only have observed relevancy under explicit user engagement events. In order to estimate expectations on counterfactual quantities using observational data, we invoke regression adjustment techniques from Potential Outcome Modeling Framework 39. The core component in this technique is to control for the presentation-based confounders, e.g. the rank of the items, which affect both the observed outcome and the observation event. Let comma be the causal covariates to predict the relevancy of in the search context, and let comma be the presentation-based confounders. Controlling for confounders and making inference from observational data amounts to justifying a few technical conditions. Specifically, we have to ensure a. Ignorability, that there is no unmeasured confounder left out from the covariates comma, as well as b. Overlap, that for any feasible value of covariates, the probability of observing the relevancy of an item given the covariates, i.e., the propensity score, is bounded away from 0, O equals 1, 0. Moreover, we have to make sure that the definition of the observation event is c. Stable in the sense that the potential relevance outcome of an item does not depend on whether the other items are observed. We can then compute the expectation of the outcome of counterfactual relevance using iterative expectations on observational data 39 using R, OD equals 1. D equals C DOD equals 1, XDS, ZDS, 10. Where the observational expectations on the right-hand side can be estimated via a machine-learned classifier trained on a dataset of items with explicit engagement events using a cross-entropy loss 4, 9, 3. Assuming that the presentation bias is primarily signified in the rank of the items in the page, a vanilla instantiation of this approach is adopted in 3, where the relevance probability is estimated as the observational click probability in rank 1. That is, R equals 1, equals, C equals 1, equals 1. Similarly, in the GBDT-based approach in 17, the model is trained with an interaction depth of 1 to avoid interactions between the rank and the relevance feature, and at the inference time all the trees that use the rank feature are removed. In the two-tower approach in 4, a counterfactual model is developed via independent relevance and observation towers, and only the relevance tower is used for inference. A similar approach 8, which we adopt in our empirical experiments, follows this perspective by training a model on a cross-entropy loss between the IPW-debiest empirical, Bernoulli, distribution of clicks and the relevance distribution defined by the predictor, that is, 1 sigma set membership symbol sigma, IPW. 11, 3.2.2. Relevance teacher trained on expert judgments. In contrast to the relevance teachers trained on the observed biased feedback, discussed in the previous subsection, we can train teachers based on relevance labels provided by expert judgments. The fundamental premise of such relevance teachers is to approximate the marginal query-based relevance probabilities via expert annotated labels that are assumed to capture the canonical intent of a given query.
Okay,
Knowledge distillation is crucial in this case,
so, okay, what is it?
because the student...
Okay, it's not that complicated, by the way. It's not that complicated. Don't panic. So we wanted to do knowledge distillation, purify knowledge. Also, we know that it is about ranking. All right. It's about ranking. We know, okay, to keep it simple. And what they do for distillation is that they use teacher-student method. And it is teacher-student method is easy. You know what it is? When sometimes we have a large data set, right? So we can train a complex method on it. Let me use my both hands. We can train a large machine learning model on it. It's called the teacher. But we cannot apply this machine learning for our predictive prediction task. Why? Because it takes a lot of energy, it takes a lot of computational resources. Therefore, we are trying to come up with a simpler learning model, which is called student model. The student model will do the same, but it comes from the teacher, and distillation is done when we use our student model. That's it.
Does not have access to such judgment-based labels in its own training data, and the relevance teacher trained on these labels is not strong enough as a standalone ranker, because it cannot take advantage of the more granular preferences in user engagement data. Another important advantage of using relevance teachers trained on expert judgments is that we can use a broad range of pooling techniques, including active learning, to collect judgments on queries for which we do not have rich user engagements, alleviating the selection bias inherent to all the methods discussed so far, which rely strongly upon implicit user feedback. In the next section, we provide strong empirical results by adopting such relevance teachers. For empirical results and discussions, we evaluate the performance of the proposed empirical risk estimator by adopting a standard supervised counterfactual training and evaluation framework on real-world user behavior data collected from online traffic. For empirical...
If I'm standing, I cannot do that, but if I am like running, I can do that for sure. Okay, I can't do that. Even standing, I can't. Oh, bitch. Another time. Okay. Now I'm fully awake. Oof, my heartbeat.
Results and discussions.
Let's go. I don't
We
want to sit
evaluate the
down.
performance of the proposed empirical risk estimator by adopting a standard supervised counterfactual training and evaluation framework on real-world user behavior data collected from online traffic of a major e-commerce platform. We also report the results from an online randomized control experiment on a model trained on a distilled empirical risk estimate to showcase the generalization power of the proposed techniques from a rigorous causal evaluation perspective. For completeness, we also conduct offline counterfactual experiments on standard academic datasets generated via synthetic user behavior data generation on human-judged web search data, following the simulation setup and code from A. Since the focus of the paper is on the incremental value from distilled empirical risk minimization techniques to control the estimation error in LTR, we are oblivious to the experiment design choices related to approximation error, optimization error, and parameter estimation techniques for the observation model. As such, we fix the
Doesn't have a
hypothesis
battery,
class,
that's why
model
it's not working.
hyperparameters, training optimization techniques, and estimated/simulated propensity scores across all estimators and limit the set of baseline models accordingly.
By the way, look
For the
at
synthetic
the
data sets,
hands.
we describe the
Hands are
details of the
hands of
experiment
other
setup only briefly and
So
refer the reader
dirty.
to aid for extended discussions and alternative choices, data synthesis choices, and propensity estimation techniques. For experiments on the proprietary e-commerce setting, we only
Proprietary.
report lifts compared to a standard simple baseline, with a focus on the choices relevant to the estimation error, oblivious to model training and propensity estimation techniques. 4.1 Experiment setup for synthetic data sets. Dataset semantics. We use publicly available datasets with manual relevance labels Yahoo Web Scope 40, MSLR Web 30K41, and Istela S Letter 42
Dude,
and
that's such an
synthesize.
interesting way That's actually very interesting, right? Because in physics, in the past, or like other branches of science, we always had experiments in biology, in chemistry. So somebody in the lab did the chemistry, did the experiment, and then come up with a result. Probably they had different experiments, each one has something different from the other. Now in computer science, we need to work with data, but sometimes we need to build the data ourselves. So we need to have a good set of what is our data sets, what are the standards for a data set, and it's here.
User engagement labels with standard logging policy and user behavior generation semantics, following a 1. User behavior model. We use
How
a
can I
vanilla
open
position
it
bias
without
based
breaking
examination model with the observation probability, O equals 1 rank, equals, 1 plus, rank 1, / 5, 2, ignoring the trust bias. We also use the same clipping function used in 8 to control the variance of the simulated click propensities. Moreover, we assume that the parameters of the propensity model are known and need not be estimated. Since user behavior modeling and propensity estimation are not the focus of this paper, we avoid unnecessary comparisons with more complex techniques in the literature. Estimators. The logging policy is trained based on a standard supervised training on 1% of training data using an empirical label distribution based on the available relevance judgments. The logging policy is assumed to be deterministic. The naive estimator is trained on the biased empirical click distribution without any corrections, and the IPW estimator is trained via 6, using the actual propensity scores used for data synthesis. For all distilled risk estimators, we use the same pre-trained deconfounding teacher model, 1, trained based on the IPUDA biased empirical distribution via the point-wise cross-entropy loss, discussed in 11. The KD1 is trained via 7, and the hybrid estimator HD1 equals 1 and the doubly robust estimator R2 trained using the same teacher model 1 and the actual synthesized propensity scores, via label distributions, 8, and 9, respectively.
This one doesn't work.
Training, following
Don't ruin my
8, for the
cube, by the way.
hypothesis class, we use MLPs with 232-unit hidden layers and adopt the standard lambda loss optimization framework 43 to train the model on the proposed empirical risk estimates with equals 106 training samples randomly sampled from the synthesized data. Evaluation metrics. We use the normalized expected number of clicks as the main evaluation metric, which is aligned with the training objective. Specifically, for a given search context, with candidate set, the expected number of clicks for a policy is. By adopting the synthesized observation probabilities, O equals 1 rank, from our user behavior model as the
How can I
discount
clean
function,
it, though?
and IPW devious clicks as the relevance labels, and normalizing the contribution of individual context by the maximum attainable value, we get our primary metric, NCTR. Moreover, by adopting the original judgment-based relevance labels as relevance labels, and data agnostic standard log rank discounts for, we calculate NDCG with respect to the using data agnostic standard log
Okay, it's
rank
not
discount.
dirty, it's just the
4.2
material.
experiment set up for real-world user data.
It's just like
Dataset
salt.
semantics. We collect a dataset of around
It
1
has
M
sediment,
queries from a
so
major
it's
e-commerce platform in 2023 with a single click event attributed to the logged
Now we
SERP,
have a
oblivious
3D
to the logging
clock.
policy and the post-click engagement
Right,
events
this is
attributed
fine.
to the clicked items.
Back
For
to
training efficiency, we sample 3 negative samples at random from impressed items within each training SERP. For the test data, we use a similar query sampling strategy, but keep all the candidate items to be re-ranked by the candidate ranker. Estimators. The baseline model for all the reported lifts is trained on the naive estimator corresponding to the observed clicks, without any debiasing. The IPW estimator, and all other estimators that rely on
So
propensity
that's it,
correction.
that's what
We
happens.
use estimated
When you
propensities.
listen, you don't get involved with the paper, that's what you understand. You don't understand nothing from the paper. Good
Using
luck.
the standard regression-based expectation
It's not,
maximization
papers
techniques on
are
a
not
vanilla
written in a way so
examination-based
that you
position
can
bias model
understand them
17.
easily. You get
The
it?
teacher
That's
models
the
are
art of a
trained on a predictive
PhD
task with a
student.
cross-entropy loss over datasets with different distributions. The deconfounding
That's,
teacher,
by the way, super
1,
stupid. I
is
think
trained
they
based
can
on the IPW-debiest empirical distribution
talk
of
about
labels
these
for
bullshits over.
query item,
Okay, by the
pairs
way,
with
I
the
want to
same
work with this
representation
guy. I
as the
better
ranking
not say
task
so many
sampled with
bullshit
more
words.
stringent conditions to ensure that the
Let's see if
relevancy
they
of both
have
the
a
positive and negative
presentation on
items are
YouTube.
observed,
You know
satisfying the
what? This is
conditions
not their
explained in
problem.
section
You know,
3.2.
this is a general problem we have. Is that we are still sticking to papers. Fuck papers. Counterfactual learning to rank via knowledge distillation. Every paper nowadays should have a video on YouTube. And this, I mean, you can have the paper, but it should not be the main thing that you do. You know? What is it? Counterfactual learning to rank via knowledge. What was the counterfactual, by the way? I missed that part. Counterfactual. We learned the student, we learned distillation, we learned material phases, but learning to rank, but I missed the there is nothing. That's nice. What are these? There is nothing else. I think writing
Point 1 for
papers,
training
we should make
counterfactual
movies
models
from
using
now on
observational
in
data.
academia. Movies are also too long.
Specifically,
We need
for
to make movies, we need to make YouTube shorts. That's what
positive
we want to do.
examples, we require that there has to be an engagement event with shopping
No,
intent
people
associated to
find-
the item,
people
and
know
for
what's
negative
going
items
on
we
in
require that they appear
academia.
above the last engaged item in the SERP. The relevance teacher, 2, is trained via expert judgments trained on query item, pairs with binarist relevance annotations, which satisfies stringent calibration properties. We are oblivious to the data pooling and training
You are
techniques used to
oblivious.
train this teacher.
I'm not oblivious.
The hyperparameter of the hybrid estimators is optimized via grid search on the NCTR objective.
Observant.
Evaluations, for offline experiments, we use NCTR with respect to IPW-debiest clicks as relevance labels and a simple rank fit on the estimated propensities. We also use NDCG with respect to naive clicks as a vanilla evaluation metric. For online experiments, we report ranking efficiency metrics in terms of concentration of engagements in top slots, DCG, as well as the cumulative reward metrics with respect to the share of search result pages with an engagement event, CTR, from a randomized controlled experiment on the online search traffic of a major e-commerce platform. 4.3 Empirical research questions. Results and discussions on synthetic data. Table 1 provides an overview on the performance of the estimators of interest, for evaluation metrics, specified as meta-columns, over the evaluation data sets, specified as columns. We observe across all data sets, that the IPW outperforms the naive estimator and all distilled estimators outperform IPW. An extended discussion on the performance of the IPW and DR1 can be found in 8 with interesting variance analysis. The most interesting observation is that the pointwise counterfactual click prediction teacher 1 exhibits a strong ranking performance when it is used as the only target component, which is aligned with the results from 8 where it is used as a standalone ranker. This observation signifies that there is no meaningful heterogeneity in training data distribution across search contexts in these public datasets, and strong ranking performance can be obtained without having to resort to list-wise modeling. There is barely any performance gain in using the doubly robust estimator, and we omitted doing any parameter tuning for the hybrid estimator. Counterfactual evaluations on product search data. Table 2 provides relative performance lift of the candidate estimators against a naive click model baseline. In stark contrast,
counterfactual.
Table 1 performance
By the way, we are
evaluation
going
of the
to play
candidate
Counter-Strike
estimators in
after
full
this.
ranking setting. There is no display
looks
rank cutoff,
shitty.
with known propensities
I
using
mean, you
equals
cannot listen to a
106
paper. It's
simulated
not
training
designed to
queries,
listen to.
evaluated over
It's not an
20 runs
audio
over the
book.
test data set, following a
But honestly, we
the minimum
need that.
detectable
We need
effect size
every
given the
fucking
size of the
paper,
90%
we need an
confidence
audio
intervals from
version.
this
What
experiment
if
is
somebody
around
is blind? What?
0.005.
We need some video version.
NDCG,
Why are
NCTR
we
Yahoo,
sticking to
MSLR
papers?
Istella Yahoo.
This is so stupid. Nobody
MSLR
reads
Istella.
paper.
Logging 0.858,
I don't say
0.748,
don't have papers, but you should have other things too.
0.758, 0.498, 0.703 naive. To the results on synthetic data sets, we observe that the point-wise teachers are not very effective for the ranking task due to heterogeneity in the training data distribution. This is
Actually,
because
I need to
point-wise
open
models
my
focus their
journal.
predictive
Journal
power also on
audio.
learning that some contexts are
Actually,
inherently
like,
easier
I don't
slash
know, what
harder
is
for
it?
relevance
Simon,
or engagement
student,
prediction
Berkeley,
tasks.
Stanford,
Although
MIT,
the
they
Bayes
put a lot
optimal
of their
relevance predictor
seminars
is also
online.
Bayes optimal for list-wise ranking
Should be
loss
like that.
44, when learning a
Good job.
contextually discriminative
Do it
and
more.
well-calibrated relevance model is
Do that
complex,
more.
such models fail to perform well in the ranking task. The performance gap, not reported in the table, is even higher for the relevance teacher trained on expert judgments, particularly because the model is primarily focused on the context affinity of the candidate items rather than historic performance. We observe, however, that the hybrid risk estimators base the relevance teacher outperform the IPW estimator. It is interesting that the relevance teacher trained on expert judgments significantly helps with the performance of HD2, signifying the importance of soft relevance labels for all candidate items and the synergy between the relevance annotations and the implicit user feedback. We note that the DECON founding teacher 1 helps only marginally with the performance of the HD1 estimator compared to the IPW baseline. Despite the theoretical appeal, the empirical performance of the doubly robust estimator relies on effective assumptions on observing the relevance of the unengaged items. In fact, as demonstrated in the table, the doubly robust estimator based on the naive observation assumption that relevance is observed only in the event of explicit user engagements, fails to outperform even the IPW estimator in terms of ranking efficiency metrics. Online experiments on product search ranking. In section 3.2.2, we argued that a relevance teacher can help not only with better generalization, but also with alleviating selection bias of the ranker by further incorporating queries with poor engagement history in training. We also showed strong empirical results from offline counterfactual evaluations that incorporating relevance signals from a relevance
really
teacher,
nice. That's
trained on
amazing
expert
about
judgments, in a hybrid distilled risk estimator can significantly improve offline SERP efficiency metrics. To support our claims on the generalization power of our proposed estimators, we report the results from a controlled randomized online experiment in a major e-commerce platform, where the relevance ranking. Table 2 relative performance evaluation of the proposed risk estimators compared to a naive click-based estimator as baseline, with 90% confidence intervals based on bootstrapping on a test dataset of size equals 105. The effect size of a lift is deemed meaningful if greater than 0.3%. Delta, NDCG, naive, delta. Model is replaced with a model trained on a hybrid distilled risk that relies both on Debias user engagement events and a relevance teacher trained on expert judgments. Beyond significant lifts, plus 2%, in search efficiency metrics as measured by rank discounted measures, we observed a remarkable lift, plus 1%, in click-through rate, confirming generalization in terms of converting more novel queries, as well as 0.5% reduction in search abandonment rate, which is mostly affected by hard queries with poor historic engagements. 5 Concluding remarks. We proposed an effective debiasing technique for counterfactual learning to rank from observational search activity data by using distilled knowledge from a relevance teacher to inform the label distribution for a list-wise ranking task.
Damn,
We
I
established the
feel the pulse.
generalization power of the proposed estimators through rigorous empirical results in offline counterfactual evaluations as well as online randomized controlled experiments on a ranking task in a major e-commerce platform. We also presented a theoretical analysis of the estimation error of the proposed estimators to justify the improved generalizations from a theoretical perspective. Our contributions highlight important insights into using potential outcome modeling from the more generic perspective of knowledge distillation.
By the way, when I say movie, we should definitely do that. Or we should definitely put audio files about our research. This way it takes more time of us, which is better because we publish less. You look at the scientists, they publish, oh my god, 10,000 papers. And dude, if just there was only you on the face of the planet, nobody else was into writing paper. Nobody had the time to read all of your papers. What are you doing? You don't remember what you published. What is happening? The guy has 10,000 citations. Well, that shows that you should do something else probably. Let's rule, guys. Let's rule. Let's roll or let's rule. Let's rule and roll. Roll and rule. There is nobody? Wait, what? Dude, did you see that? The bullet does not go in a direct way. It's not go. First time I noticed, it doesn't go in a straight line. Oh. Dude, come on. Dude, leave me something. Woo! Your ass is burning, bro. Haha. Oh. Ooh. Ow! Okay, like 3 times. If I deserved it, I deserved it. Which where are you from? By the way, we play 2 rounds. We play 2 rounds. Yes, this is a complete round. Dude, fuck off. I felt I hit his face. Could feel it. Ah. Who is this big bot? What is happening? What is my gun? Where is my fucking gun? What the fuck? I was looking for my gun for 2 hours. Oof, look at my speed. You can see that this gun is light. Ooh, bitch, not beach. Oh, fuck. Sucks when a bot has the gun you have. Wait, brother. Oh. Okay. Fuck you. Come here, bitch. 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 Where are you going? Oh fuck. Not. Let's finish it. There are people showing up and stuff. Let me. Dude, this guy and I have the same guns. Oh, who got the? Who? In our team? Okay. I like pool. Actually, recently I like pool more.
Shut the fuck up, you fucking retard. Go get a fucking job, you incestual fucking crack baby dumbass bitch. Get mad.
How do they
Go hang
talk?
yourself, dumbass. Buy a fucking rope ASAP. Mirror.
I wish I could talk. I don't know how to speak. There should be one of these. I will check it next time. Ooh, all of them are kids. Oh my god, they will. Okay, all are people now. Wait, what? Oh, okay. Shoot, bitch. Oh. That's why I like pool more now. You get it? Oh. Back door. Okay, motherfucker. Let's go, guys. I'm gonna kill you like you don't, like you deserve it. Let's go. That was fun. Let's go this side. They are coming here. Fuck. You're dead? What? Snipe? Bitch. Where are you? This is cool about. Cool. Oh shoot! How did he kill us? Oh, left, guys, on the left. These motherfuckers are all on the left. Oh shoot! I knew it. Oh, okay, damn. Which? From over there. From over there. Oh my god, they're even better. Oh, fuck you! No, don't kill me, don't kill me. Fuck, what a stupid mistake. Ah, no, Thank you so much. Get me. Ah, fuck no! Ooh. Dude, don't kill me. Ah. Okay, I was pretty good.
It's not fair.
How
I
do you
literally
talk?
just joined like 3
You
fucking
should quit
seconds ago.
again, you fucking whiny bitch.
How can I talk? Guys, be polite.
Why are you talking shit to me, bruh?
Cause you're fucking annoying.
What do
You are
mean?
fucking, you know.
You won't shut the fuck.
What did I do? How to... I want police. No.
Yo, have you been schizoing the fuck out this entire time talking to yourself, brother? I've been gone.
No, you're not that important.
They're really good.
Holy fuck.
Fuck off! I don't want to hear you. Alright guys, you're talking too much shit.
Wait, I'm on.
You're lagging the fuck out, shut up.
Fuck off! Who is shooting? Bro, I need some shoot. Shit. Who's shooting me? I killed. Ah, fuck. Okay, guys, we need to act better. Shit is going to be stupid. We haven't killed anybody yet. What is wrong?
here.
Yeah, I'm so exposed. Ah, fuck! Ike! How can he kill me with that? I cannot kill him with sniper. Dude, that motherfucker has something in it. It's not fair. Who is shooting? What is this line? Fuck off! This is so fake. Ah, in his face, actually. Fuck it, I'm winning this way. Where are people? And the sniper killed me. Among all of these, the sniper killed me. Dude! Let's go, bro. Two of us. Ah, fuck you! Why did you change? Getting, brother. Good job. Ooh, okay, this. Oh, shoot. This. Okay, perfect, though.
Dude, that would be funny. Sucks so much ass.
Who has the
Fucking
fucking...
your lag, yeah, say again. Can you repeat that? You're lagging the fuck out, dumbass. Fire from the fucking computer, you retard. Holy shit, you're such a fucking loser.
What is happening? Dude. Peter Pan. Fucking Peter Pan. Dude, okay, I cannot continue that. Fuck, I was so bad. Okay, let's go food one more time and I'm out. I said I have 2 rounds, but this round, honestly... How can we have 7 out of 6? Damn, that I was so bad with my first snipe. It was stupid. The sniper, yeah, I was pretty good in the sniper. Well, actually, it's my 4th round, I guess. Yeah. This is my 4th round. Sorry, guys.
too easy.
Fuck off, you. It's all your fault, motherfucker. Parking. Oh, bitch. Did you like it, Dad? Thank you. God, dude! Come on! Shit, now the game will be very difficult for me. Okay. Woohoo! Bitch! That was such a duel. Alright, bitch. I cannot come here. I love those. That was so awesome. That was so fucking awesome. Let's go, bro. How did he kill me, by the way? Oh, shoot. So they're on the right. Ah! Dude, wow, they are so fucking good. Oh, what about that? How many? Dude, okay. I'm in the baggage mindset. No, it is different game, dude. This is a different game. This is a game based on peace and height, stealth. I knew something. Guys. Don't knife me, motherfucker. Oh fuck, dude, they're. Oh shoot! Both sides. Oh my god, this is stupid. Wanted to knife me. Guys, take control. Fuck. This shit ain't finished. We need to hold our ground. Okay, let's go right there. Oh shoot, it's empty. From behind. What is this? Is it skiing? What's that? What's that? Ooh. That's the shit show! These motherfuckers cannot just. Dude, let's pull it all the time. This is just the funnest game. Funnest game, honestly. You just. Alright, guys.